Hello students, welcome to the lecture on functions and graphs, and after this lecture we will be able to learn the following objectives. Define the function, discuss the restricted domain and range, explain the types of functions. Let's start with the concept of functions and graphs. The graph of a function can give us a great deal of information about the function. We will use the graph of a function to evaluate the function, find the x and y intercepts if any, the domain and range, and determining whether the function is increasing or decreasing, an important idea in calculus. To say that f minus 3 equals to 1 means that the point minus 3 and 1 is on the graph fx. If f4 is a point on the graph of fx, then f5 equals to 4.
The idea here is to demonstrate how to make the graph of an algebraic function. Graphs are nice because they allow us to visualize what is going on. Is the function negative, inverse, flat, going up, down? In other words, graphs of functions let us see how variation is taking place. This specific graph shows production over time, and this one learning over time. Both functions show the rate of change at different intervals or points. They also show the limits of the function. In any case, to make the graph of a function, we start with the standard coordinate system and plot the data using a table that shows both the independent variable x and the dependent variable y, where x is the domain and y the function of x, or range. For example, graph the function f of x equals x squared. We first build a table of values. When x is 0, the function of x is 0 squared or 0. When x is 1, the function is 1 squared or 1. When x is 2, the function is 2 squared or 4. When it is 3, 3 squared or 9. Now, going into the negative values, when x is negative 1, the function is 1 because negative 1 times negative 1 is 1. When it is negative 2 times negative 2 is positive 4. The value of x of negative 3 will give you the positive 9, and so on. Now, if we plot the coordinates of the various points found, we notice that the function is curved, that it begins at an undefined negative value, turns around at 0, and, never being negative, turns positive towards, again, undefined values. Now, if we want to know what is happening as it turns at 0, we have to find values for the function for fractional values of x, so that when x is 0.5 or negative 0.5, the function is 0.25 on both sides of the y-axis. 0.5 times 0.5 is 0.25. We now draw the line of the graph of the function f of x equals x squared. If we want to make the curve really smooth, then we would have to compute more points to certify that the function follows the shape of a parabola. Another parabola forms when we plot the function f of x equals negative x squared plus 2x plus 3. First, we build the table. When x equals negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. Before we start, we can factor the trinomial to find where the parabola crosses the horizontal axis. We write negative x squared plus 2x plus 3 and factor the negative 1 attached to x just to make things more familiar. We get negative x squared minus 2x minus 3. We factor the trinomial into two binomials, x minus 3, x plus 1. Don't forget the negative sign that has been factored. We solve both binomials when they are 0 and x equals 3 and x equals -1. These are the points where the line crosses the x-axis. Please notice that sometimes the x-intercepts are not found by simple factoring, and the quadratic formula must be used. To review the quadratic formula, please visit YouTube and write on the top line, Jerry Levada quadratic formula, or use the following URL link. Now let's go back and complete the table. When x is -3, the function is -12. At -2 is -5. At -1 is 0. At 0 is 3. At 1 is 4. At 2 is 3. At 3 is 0. At 4 is -5. And at 5 is -12, and so on. Now, if we want to know the exact value of the vertex, we apply the equation x equals -b over 2a, and we use the coefficient shown as reference in the standard parabola equation. By the way, if you want to see how the vertex equation is found, please visit YouTube and write on the top line, Jerry Levada, vertex of the parabola, or use the following URL link. In this case, b equals 2 and a equals -1. The x value for the vertex is -2 over -2, or +1. We now solve the original equation to find the value of y when x equals 1. But we see that the table already has it at 4. So the vertex of the parabola is at 1, 4. We now plot the equation.
Intercepts of a graph. The graph also shows the intercepts of the graph. Remember that an x-intercept is a point where the graph touches the x-axis, and the y-intercept is a point where the graph touches the y-axis. The vertical line test. An equation gives y as a function of x, means that for every x value, there is a unique y value. From this fact, we can look at the graph of an equation to decide if the equation gives y as a function of x. If an x value has more than one y value in the equation, then there will be more than one point on the graph that has the same x coordinate. A line through points that have the same x coordinate is vertical. This is the idea behind the vertical line test. The graph of an equation passes the vertical line test if every vertical line touches the graph at one point or not at all. If so, then the equation is a function. Function. Mathematical modeling is an attempt to describe some part of the real world in mathematical terms. Our models will be functions that will show the relationship between two or more variables. These variables will represent quantities that we wish to understand or describe. Examples include the price of gasoline, the cost of producing cereal, or the number of video games sold. The idea of representing these quantities as variables in a function is central to our goal of creating models to describe the behavior. We will begin by reviewing the concept of functions. In short, we call any rule that assigns or corresponds to each element in one set precisely one element in another set a function. For example, suppose we are going a steady speed of 40 miles per hour in a car. In 1 hour, we will travel 40 miles. In 2 hours, we will travel 80 miles, and so on. The distance traveled depends on the correspondence to the time. Indeed, the equation relating the variable distance, d, velocity v, and time t is d equals to vt. In example, we have a constant velocity of v, which is 40. So d equals to 40t. We can view this as a correspondence or rule. Given the time t in hours, the rule gives a distance of d in miles according to d equals to 40t. Thus, given t equals to 3, d equals to 40 into 3, which is equal to 120. Notice carefully how this rule is unambiguous. That is, given any time t, the rule specifies one and only one distance d. This rule is therefore a function. The correspondence is between time and distance. Often the letter f is used to denote a function. Thus, using the previous example, we can write d equals to ft, which is equal to 40t. The symbol ft is read f of t. One can think of the variable t as the input and the value of the variable d equals to f of t as the output. For example, an input of t equals to 4 results in an output of d, which is f of 4, which is equal to 40 into 4, which is 160 miles. Let us now discuss the functions. A function f from a set of elements x to a set of elements y is a rule that assigns to each element x in x exactly one element small y in y. One way to demonstrate the meaning of this definition is by using arrow diagrams. F x to y is a function. Every element in x has associated with it exactly one element of y. G x to y is not a function. The element 1 in set x is assigned to elements 5 and 6 in set y. A function can also be described as a set of ordered pairs xy such that for any x value in the set there is only one y value. This means that there cannot be any repeated x values with different y values. The examples above can be described by the following sets of ordered pairs. The definition we have given is a general one. While in the examples we have used numbers as elements of x and y, there is no reason why this must be so. However, in these notes we will only consider functions where x and y are subsets of the real numbers. In this case, we often describe a function using the rule y equals to f of x and create a graph of that function by plotting the ordered pairs x f of x on the Cartesian plane. Function notation. Functions play a crucial role in mathematics. A function describes how one quantity depends on the other. More precisely, when we say that a quantity y is a function of a quantity x, we mean a rule that assigns to every possible value of x exactly one value of y. We call x the input and y the output. In function notation, we write y equals to f of x. Since y depends on x, it makes sense to call x the independent variable and y the dependent variable. In applications of mathematics, functions are often representations of real-world phenomena. Thus, the functions in this case are referred to as mathematical models. If the set of input values is neater set, then the models are known as discrete models. Otherwise, the models are known as continuous models. For example, if h represents the temperature after t hours for a specific day, then h is a discrete model. If A is the area of a circle of radius r, then A is a continuous model. There are 4 common ways in which functions are presented and used: by words, by tables, by graphs, and by formulas. Look at the screen for an example and its solution. Thus, we have a relationship between the quantities C and P such that each value of P determines exactly one value of C. In this case, we say that C is a function of P. Describes this function using words, a table, a graph, and a formula. Let's look at another example. The income tax T owed in a certain state is a function of the taxable income I, both measured in dollars. The formula is T equals to 0.11I to 500. Expressed using functional notation, the tax owed on a taxable income of $13,000 and then calculate that value. Explain the meaning of T, 15,000, and calculate its value. Look at the screen to understand the solution to this problem. So far, we have introduced rules between two quantities that define functions. Unfortunately, it is possible for two quantities to be related and yet for neither quantity to be a function of the other. Next, suppose that the graph of a relationship between two quantities x and y is given. To say that y is a function of x means that for each value of x there is exactly one value of y. Graphically, this means that each vertical line must intersect the graph at most once. Hence, to determine if a graph represents a function 1 uses the following test, the vertical line test. A graph is a function if and only if every vertical line crosses the graph at most once. The vertical line test and the definition of a function. If a vertical line cuts the graph more than once, the graph could not be the graph of a function since we have multiple y values for the same x value and this violates the definition of a function. Example, which of the graphs A, B and C in the figure represents y as a function of x? Carefully look at the screen to understand the solution. Now moving on to the next topic, we will study the restricted domain and the range function. The domain of a function is a set of all the allowable x or input values. By using the word allowable, one could assume that there are some values which are simply not allowed into the function. Think of a function as a mathematical machine that does something. Now, look at the screen for an example. Can you see that if you let x equals to 4, the denominator will be 0? Sometimes it is too difficult to determine the domain by inspecting, so we use a kind of reverse logic. We set the denominator equal to 0 and solve in order to find the values of x which would make the bottom 0. We then do not let these values of x into the domain of the function. Find the domain of the function given on the screen. We cannot let the bottom equal 0, so we will set the bottom equal to 0 to find the values of x we will exclude from the domain. These values of x would make us divide by 0, so we do not let them into the domain. We do not allow any value of x which would cause us to take the square root of a negative number. The range of a function. The range of the function is the set of resulting y or the output values. Let us now look at an example. Find the range of the functions as shown on the screen. First, note that the domain is the set of all real numbers. We shall let any real numbers into this function. We do not need to worry about the denominator becoming 0 since there is no division. We also do not need to worry about taking the square root or even root of a negative number since this function does not involve radicals. We shall make a table of values and then analyze that table according to the definition of the range given above. Let's now know the types of function. In mathematics, a function is a relation between a set of inputs and a set of permissible outputs with the property that each input is related to exactly one output. Let us now talk about each of them. Linear functions. A linear function is a function of the form fx equals to ax plus b, where a and b are real numbers. Here, a represents the gradient of the line and b represents the y-axis intercept, which is sometimes called the vertical intercept. What will happen if we fix b and vary a? Let us try some examples. Since the functions we are looking at are linear, the graph will be a straight line. So, we only need 2 points to be able to draw the line. However, we generally choose 3 and the third point is a good check that we have not made a mistake. Cost, revenue and profit. Any manufacturing firm has 2 types of cost, the fixed and the variable. Fixed costs are those that do not depend on the amount of production. These costs include real estate taxes, interest on loans, some management salaries, certain minimal maintenance, and protection of plant and equipment. The variable cost, it depends on the amount of production. They include the cost of the material and labor. Total cost, or simply cost, is the sum of the fixed and the variable cost. Cost equals to variable cost plus the fixed cost. Let X denote the number of units of a given product or a commodity produced by a firm. Notice that we must have X greater than 0. The units could be bales of cotton, tons of fertilizers, or a number of automobiles. In the linear cost model, we assume that the cost M of manufacturing one unit is the same no matter how many units are produced. Thus, the variable cost is the number of units produced times the cost of each unit is given as shown on the screen. If B is the fixed cost and C of X is the cost, then we have as shown on the screen. We see that the y-intercept is the fixed cost and the slope is the cost per item. In the linear revenue model, we assume that the price P of a unit sold by a firm is the same no matter how many units are sold. This is a reasonable assumption if the number of units sold by the firm is small in comparison to the total number sold by the entire industry. Revenue is always the price per unit times the number of units sold. Let X be the number of units sold. For convenience, we always assume that the number of units sold equals to the number of units produced. Then, if we denote the revenue by R of X, it is given as seen on the screen. Since P is greater than 0, we must have R of X greater than equal to 0. That the straight line goes through 0, 0 because nothing sold results in no revenue. The slope is the price per unit. Regardless of whether the models of cost and revenue are linear or not, profit P is always revenue less cost. Thus, profit P is given by as shown on the screen. Recall that both cost C of X and revenue R of X must be non-negative functions. However, the profit P of X can be positive or negative. Negative profits are called losses. Now, let us look at an example. Cost, revenue and profit equations. A firm has weekly fixed cost of $80,000 associated with the manufacture of dresses that cost $25 per dress to produce. The firm sells all the dresses it produces at $75 per dress. You have to find the cost, the revenue and profit equations if X is the number of dresses produced per week. Make a table of the values for cost, revenue and profit for production levels of 1,000, 1,500 and 2,000 dresses and discuss what the table of numbers is telling you. Look at the screen and understand the solution. Now, in the end, let us summarize what we have learned in this lecture. The graph of a function can give us a great deal of information about the function. A function is a technical term that is used to symbolic relationship between variables. Mathematical modeling is an attempt to describe some part of the real world in mathematical terms. A function is a rule that relates how one quantity depends on other quantities. The domain of a function is the set of all possible input values, usually x, which allows the function formula to work. The range is the set of all possible output values, usually y, which result from using the function formula. A linear function is a function that can be expressed in the form f of x equals to ax plus b, where a and b represent real numbers.